I really appreciate. You know, guys, the reason I forgot this semester, really, I don't forget about the recording, but the problem for this semester is before this class, I had three classes, and those classes, since something lower division, and we are not allowed to record and post the videos, so just we cannot record the video. Therefore, when I reached to this class, since I was teaching those three classes as a just routine, and I habited those classes, then I forgot about to record this class. So again, thank you so much for this point, and just let me know in future if I forgot. Thank you. So again, so let's just see, we are officially recording, and okay, we have these connections and with this information, and now we want to find the stresses at each element, right? These are the connections. Sigma ultimate for the stress, shear stress, normal stress, and these are the factor of the safety. And now let's go to the first for the find the tension in steel, right? So we should do this. So for each element, we should find the maximum tension, maximum the tension stress, and then compare with the allowable, right? So here, this is the cross sections of the steel, and the steel, if you look at the cross section, is 4" by 1/4 inch, right? This is the thickness of the steel, and from the other view is 4" right? So you can do 3D dimension here, but at this position, at this location, actually, we have a bolt. Therefore, then these two bolts makes the hole in this section. Therefore, we don't have the steel here, right? We don't have a steel here. Therefore, just this piece, this piece of the sections contribute to the stress, right? So again, the cross sections of steel is 4" by 1/4 inch, right? 4" by 1/4 inch. And then, since we have the two hole here from the bolt, so we don't have a steel here, it's removed, just these three pieces. So let's find this area. So this area would be the area of the steel minus the diameter times thickness of the bolt. So 4 times 1/4, that's the whole cross sections, minus this diameter times thickness, and this 2, since we have two holes from the two bolts, right? Like that. So the P is that this force makes the tension at the steel also. This is a force because of the equilibrium. We have also the reaction of this force on the wood, on the steel. So it makes the tension in that section. So then the sigma would be 19,200 PSI, right? And now it's the time to compare with the sigma allowable. So sigma allowable, in the last lecture, we said the sigma ultimate, sigma y or sigma ultimate, divided by factor of the safety. So let's go back. Still, sigma ultimate for the steel is 36. Factor of the safety is 1.75. Just for bearing, it said use the 1.25. For the tension, use the 1.75, right? So we use 1.75. The sigma allowable would be 20.6 KSI. So it's good. 19.2 less than 20.6. 19.2 less than 20.6. So which means this steel plate under the tension is fine. It's fine because it's less than sigma allowable, right? So that's about tension in steel. Let's find tension in wood. So again, that's a wood. So what's the cross section for wood? Is 4 inch by 2.5. For a steel, that was 4 inch by just this thickness, but for the wood, 4 inch by 2.4. This is a 3D dimensions, right? This is a 3D dimension. So this is one side, this side, and this side is this, right? So again, we have two holes here. So 12,000 is force, 4 times 2.5 minus 3/4 this times 2.5, and this 2 means since we have two holes here. So then we consider just these 3 pieces, just in the sections of the wood in the place of the bolt, right? Which means this section that contribute in the tension. The answer would be 1920, which means 1.92 KSI. Let's compare with the allowable stress. The sigma ultimate for the wood is given, is 4 divided by factor of the safety. It's 1.75, it's 2.29, and that's fine, right? 1.92 less than 2.29, right? That's a tension in the steel and wood. So which means tension stress is satisfied. So there is no unsafety for just for the tension.
Professor, I had a question about the area. So
Yeah.
the holes that we're subtracting are technically like cylinders, right? How come we don't use like pi for the area of those holes?
Pi, you said?
Yeah, so I mean,
Pi,
they're technically
pi is here. We wanna just, because the force is applied here, pi is inside. We don't care about that. We focus on here, you know.
on the like the surface area only, kind of.
Yeah, let me draw it in the whiteboard, right? Just once
I had the same question.
Yeah, once I want to draw it, I want to draw it from the plan, not 3D. Maybe that would be the it would be clear, right? Question here is 3/4 inch is the diameter of the bolt, right? So let's just assume this is the cross sections of the. Okay, can you see this whiteboard?
Yes.
So let's just look at the top of this. I don't want to draw this tree. Just look at top of it, right? What happens if we don't have a hole, just a net area, right? For example, if we make a section here, not in the bolt, right? Just make a section here, right? So if then we have something like that, right? It's 4 inch. This is 2.5 inch, right? So this is a whole area. But now we have two hole here, which means there are bolt here, there are some bolt, there are some hole, and which means there is nothing here right now, right? So this is just this part, this 3 pieces, just wood, right? So we need to consider these 3. This part plus this part plus this. Just this piece plus this plus this. And this is empty actually. There is nothing here now. There is nothing. So now if you look at here from top, again, we have some rectangular Yes, now you're looking the 2D just now, instead of
So
3D.
yeah, so we're technically only looking at like that specific layer, if that makes sense.
Yeah, or maybe like something like that. It would be maybe better. So assume we have this force, right? Assume we have this tension force, right? Then it makes a stress just here, right? So this is nothing here. So then we assume this length minus these two pieces, right? Times thickness. This is the area contribute to the stress. So those things you see is a pi something, so we don't care about these things.
So, Professor, it's the cross-sectional area through the middle of the bolt holes, like from the top
Exactly,
view?
exactly middle. Yeah,
So then the stress that we find will, like in real world, I guess, will only be true for that specific layer. But let's say we were to go lower in the hole, then it'll be kind of different since like I guess this diameter kind of like shrinks. I don't know if that
yes,
makes
yes,
sense.
yes, the estrus is different. The reason we want to find the maximum, the critical one, right?
Yeah, because then more area, that
For
means less.
example, look at if you go to this sections, right? We have this dimension is less than that one, right? Which means more area for the wood contribute to the estrus, right?
Okay, yeah, that makes
Yeah,
a lot of sense now.
yeah. We pick the critical part. So let me back to here. So we pick at the middle of the bolt, which means we remove lots of area to find the minimum area because we want to find the maximum estrus, right? To see what's the maximum estrus in comparison to sigma allowable, right? Then if it works, therefore for the other section also works well, right?
Yeah, that makes sense. That makes
Yeah,
a lot of sense now. Thank you.
right. Yeah,
So
I know it's a little bit, it's difficult to imagine at the beginning, but just maybe this figure is always is good. Just, you know, if you have nothing, if you don't have hole, it's good. It's just T. All this is fun. If you have hole, just draw this one at the middle of the circle. And then we need this as this dimension, this for the area. And then since sigma is P over A, so here we have a whole length is contribute to area, and then we remove this part, which means we decrease the area and then estrus increase. And now it's we increase the estrus, so we should compare this one with sigma allowable, right? Does it make sense?
Yes, it makes sense. Thank you.
Okay. So this is a sigma for tension, right? So just if I give you the some details like that with the bolts and things, just make sure to calculate the stress in the place of the bolt, something like that. Because in this place, because as if you don't have this one, if you calculate here, for sure the sigma is very less than this one and the condition is satisfied. But make sure to find the stress at these sections, right? So this is about the tension for both steel and wood, but for the shear, let me before go to this calculation, just draw a figure. And because we need a little bit discuss about this one for the shear, let me go to the whiteboard. So for the shear, let me just ask you as a general case, we have maybe plate, something like this, right? Under force, for example. And then assume we have a hole here, right? If we ask to find the shear in this problem, so for the tension, so it would be the same as here, just make a section at the middle of the hole. And for the shear, we have some different scenario. For the shear, You know, once we apply the force here, the shear happens in these regions. These regions is very impractical, is very, very critical regions. Why? Because this hole is very close to this edge, right? Then if we have a huge force, we apply the huge force here, then maybe we have a crack or shear in these regions, right? So in this problem, shear area, we assume the shear area as these two areas, right? So this is a 2D figures. And now let's back to our problem to see in the 3D how can we model this, all right? So this is we have a 2 shear area, you know? So let me say something before that. In design problems, in real problem, in the design, finding this length is very, very important. Then the engineer, based on some force and the dimension, there are some tables, and say, okay, use the minimum value for the center of the board to the edge, and what's the minimum value, right? And that minimum value is based on the calculation, based on the diameter of the hole, right? So the reason behind that, those calculation is shear, is this one. And now I wanna just show you how can we calculate the stress at this region, right? So this is a 2D, it's good for a start. And now let's, if you back to the problem for the shear, it's kind of like that, right? Look at this steel. Look at this steel plate, right? If you apply the force, the reaction goes there. And then look at this edge of the steel. Look at this edge, right? From center of the ball to this edge is 1 inch, right? Then once we have a force here, this section is very critical. So we have 4 sections. It makes is play the role of the shear area, right? So 1 inch times 1/4 inch, right? Look at this piece of rectangular here, right? 1 rectangular, 2, second one, 3rd, 4th. If let me zoom in. So I hope you can see this 4, right? I show you based on the 2D dimension, and now you can see the 3D dimension. So now this 12,000 force play the role of shear to this area, and now you can see this force is parallel to these areas, right? The definition of the shear stress, right? This force is parallel to these areas. So we have 4 planes, right? 4 areas. Each one is 1 times 1/4, and 12,000 is the force. Therefore, the shear stress would be the 12,000 psi or 12 ksi. And now, yeah, just please be careful, because I saw this mistake every time when I made the problems for the test or something. Just make sure to compare with the shear stress, which means look at the problems very carefully. The problems here, shear stress is 24, it's not 36, right? Now we should compare with the sigma allowable based on that. 24 divided by factor of safety 1.75 here, right? It would be 13.7, and that's fine, 20 less than 13, right? Which means the steel plate under the shear is fine, is good, right? Does it make sense to you? Look at just direction of the force and direction of the plane would be the parallel, right?
So to my understanding, it just depends on the shape and where the shear is touching?
Yes, yes.
Okay, so if it was like for example, it was like a cylinder and then there was like a bolt going through it, that's when we use the pi. But since this is rectangular and it has bolts?
Yeah.
Okay.
Yeah. For the shear on the board, which means cylinders, I want to show you also something. Yeah. So the same as calculation, what about for wood? How about for wood here? The wood, you know, the edge of the wood is here, right? 2 inch from the middle of the bolt. So we have 4 plane. One plane here, the other plane, and 2.5 times 2. 2 times 2.5. This is a 2D dimension, this is a 3D dimension, right? Is similar to this, but for steel we have 1 inch, the 1/4 inch, but for the wood we have the big thickness, 2.5 inch times this. And you know, look at these planes are parallel to the forces, right? So these calculations would be 600 psi, which means 0.6 ksi, compared with the, okay, 2 is the ultimate shear stress divided by factor of the safety, 1.14, 0.6 less than 1.14, it's okay. It's fine. Does it make sense to you?
Yes.
I had a question on the terminology you use for the ultimate. Like in my textbook, it says I have fell. So when you say like the stress ultimate, does that mean the same thing as stress fell?
Well, yeah. Let me just let's withdraw the diagram in the last lecture, right? Or maybe you have seen the material lab, something like that, right? For example, for a steel, we have a stress strain curve like that. This is a strain, this is a stress, right? This point called sigma ultimate, which means if this one happened, then we have a fail in the sections, or we have a crack or something like that. For some problems, we assume this. For some problem, we assume this sigma yield. Yeah, if you in the textbook you see sigma ultimate or sigma fail, which means this one, right? Does it make sense?
Yeah, makes sense.
Mm-hmm. Yeah, but no worry, I will give you the value for that one. So what's the reason for using 1 inch for 1 inch for steel, 2 inch for wood? Let's see. Okay, look at here. When we apply the force for the wood, look at maybe this problem here. This problem is better, right? This section is very to the end, right? This is 2 inch. So we assume this one, but for the steel, the reaction of the 12,000 because of the equilibrium goes upward here. And then from the center of the bolt to the end is 1 inch, you know, this dimension. From center of the bolt to the edge of the plate, right? Okay. So does it make sense to you right now?
Yes.
Okay. Yeah. Just this dimension. Okay. Thank you. Okay. So that's about the shear. Let's go to the bearing for wood. So for the bearing, we should use the formula from the, again, if you remember from the last lecture, let me again just open that file. Maybe it would be helpful again. Bearing, yeah, bearing again, just as a review. If you have a bolt in the plate, the formula for area for the bearing would be thickness times the diameter of the bolt, right? We said this is a proposed formula to find the bearing once we have a bolt, the bearing in the bolt in the connections, right? So now let's go to the problem. So for the wood, we have these 2 bolts here. So the diameter of the bolt, 3/4, the thickness of the element, 2.5, right? And 2, this 2 means, since we have 2 bolts, right? But 3/4 diameter of the bolt times 2.5, which means just this area. It looks like this. Here maybe better. It looks like this area, right? But in my problem, just we inverse the plate 90 degree, and then we have this one. 3/4 inch times 2.5. So bearing is, oh, okay. So for bearing stress, make sure to use the correct factor of the safety. For bearing, it gives us the factor of the safety 1.25. Factor of the safety for bearing is 1.25, right? Just make sure to use the correct value for that, right? 1.25. So 3.2, that's okay. It's, yeah, 3.2 equal 3.2. If it's equal also, is acceptable for us because we already because the factor of safety also is one of the conservative values. If it's equal, you can accept it. Don't worry, you can accept. In reality, in the project, maybe not, but in the class, if it's equal, maybe that's okay. So let's for bearing for a steel, okay. For the steel, the only difference is thickness. Thickness of the steel is 1/4 inch. So diameter of the bolt again 3.3/4. The thickness is 1/4 inch, and 2, since we have 2 bolts, 2 bearing area, right? This 2 bearing area, and that's a problem now. It's 32 is greater than allowable stress, and now it's a good time to ask a question. So what do you think? So as an engineer, how can we figure out this problem? Because right now it's unsafe.
Need thicker steel.
Area.
Say that again.
I think we can increase the area.
Increase, you are right. Increase area. What area?
Thickness of the steel?
Thickness of the steel. That's a good thing. Thickness of the size of the bolt. That's fine because bolt. But instead of 1/4, maybe use 1/2 or something like that, right? 3/4 or 1/2, and then we need to redo again the calculation and check. Yes, right? Does it make sense to you?
Yes.
A question.
Yes.
I don't understand why in bearing you in the denominator you multiply by 2, and for shear you multiply by 4.
Here we have just 2 bearing, because we have, this is the one bearing area, right? This is the other bearing area. We have 2 bearing area. But for the shear, we have 4 plane of shear, right? Let's see, for example, let me write 2-dimension, maybe it makes more sense if we have model this problem as 2D with 2 bolts, right? So this is 1 plane, this is 2 plane, this is 3 plane, this is 4 plane. 4 plane of shear, but 2 plane of bear, right? 2 plane of bearing, but 4 plane of shear, right? Does it make sense to you?
Yes, I get it now.
Yeah, just ask me because I know it's a confusion.
I guess on the same kind of question.
Uh-huh.
So the tension, it makes sense now that like we're like kind of cutting it right in the center. But I'm kind of confused between the difference of shear and then bearing.
So for shear, shear is just because look at this plane. The easy explanation, this plane is parallel to this force, right? That's the definition of the shear. For the normal, if you remember the first lecture, for the normal, the force perpendicular to the surface, right? That's a normal.
Correct.
For the shear, the force parallel to the surface, that's shear, right? So this is a force, this is a plane, is parallel, right? That's an easy explanation for that, right?
Oh, so the bearing will be the normal?
Bearing would be kind of normal, but for bearing, as we discussed before, calculating the stress in this area is very difficult. Therefore, the standards propose, and instead of stress on this side, just assume this area. Just this
Okay,
area.
that makes sense.
Yeah.
Yep, that makes sense. Thank you.
Okay. Let's go. Okay. Yeah, just we go step by step. You understand the stress calculation at the beginning, and then the rest of this not so much. So that's about it. So again, we can increase the thickness, and then we overcome that problem. The last page, shearing bolts, shearing the bolts, and then okay, we have this bolts here, and just shear on the bolts. You have two bolts, and now I think this is one of the questions you asked me earlier. What is the area of the bolt, surface of the bolts? Pi d squared divided by 4, right? And we have two bolts, and just find the answer, right? This is the area. Okay, shear in bolts. Just make sure. Once when I asked you, it's shear in bolts, not shear in the steel, not shear in the wood. Specifically, I asked shear on bolts. So this is force, and it's parallel to surface of the bolts in the sections. So what is the area of the bolts? Pi d squared divided by 4. And shear stress is 24. Factor of the safety 1.75, then 13.7. And it's good, 13.58, less than this one. Does it make sense?
So you only used pi when it's asking for the shear and the bolts?
Exactly, shear, just shear in the bolt, right?
Okay. What
Just
about if
shear.
it was asking for bearing and bolts?
Bearing is a common surface between the element and the bolt, right? And therefore, for the bearing, we just assume this part. Bearing, we cannot see the bearing in the bolt. We may say the bearing between the bolt and the wood, or bearing between the steel and the bolt, something like that, right? For example, here, once I said the bearing in wood, which means bearing in the area between the bolt and wood. Once we said the bearing in steel means the area between the bolt and steel, right? Is a common area, right?
Okay, so it includes it in there.
Yes, yes.
Okay, thank you.
So guys, I know it's really complicated, and now the plan for today, I wanna do something like this. I have one more problem, and I would like, and actually I delete the solution. I wanna upload it now and ask you to spend some minute to solve that. This is not an exercise, because I wanna show you solution. Just I ask you, give me a tension stress, give me what's that, shear, and just spend some minutes. I want to check if you understand, or it's good practice, right? And then I can show you the solution discuss, right? Just let me. Unfortunately, I cannot find how to send the file in the Zoom, but let me just send it in the Blackboard. And then after the lecture, I will send the one with the solutions. But right now, I just wanna send you without the solution. Just let's just I put the six stress file. It's very interesting things, because this would be six practice. Let's put 6 practice. Okay, because I would like just to enjoy the class, because if I want to just 6 practice. Okay, guys, you can go to Blackboard. Can you see the Blackboard this file? Let me
Yes.
just download one of them. I don't know why it's duplicated. Just download one of them. It's the same. Download one of them. I will remove this tab later. I want to send the complete. So, okay. Let me open the file. I want to just ask a little bit about something. Just think about that. Don't afraid about the problem. You know, we have so the first page, just calculation from the statics. We have a distrust. Can you see my desktop?
Yes.
Okay, this is a truss. This is the force, and this is element AB. Element AB included two parts, right? This is the element BC, and then these are some information. This is some calculation to find the force from AB and BC. You don't need to redo that. FAB is 24, keeps tension. FBC is negative 12, 26.83 compression. And these are, again, I repeat it in every page. Just guys, so as a first step, just as easy thing, the easiest one, find the axial tension and axial compression. You know, AB is under tension, BC under the compression, right? Find the maximum one and then compare with the allowable stress. Just let's see, just solve this one. Let's see again. And axial in tension, and in the compression, right? Just find the answers. And then and also maybe shear is difficult if you want. Then at the end for the bearing, page axial and the bearing, you can just solve these two. Let's spend some time, think about that. How can, just compare with the previous examples. And I think all the figures are given. Maybe you can just imagine. Find the tension. So since we have a hole, we have a bolt, you should find the maximum stress, right? Maximum stress. Just spend some minutes on that. Spend some minutes and then give me your solution, and then I show you the problem, because this type of problems is difficult if I wanna give you as extra credit or exercise. This type of problems maybe it's confusing. You need some time, but I would like just share. And where do we say solutions? I wanna show you solution in a few minutes. I wanna show you solution in a few minutes. Just I want to ask you, first of all, think about that. Right now, 6:15 p.m., right? So think about it in a few minutes. And then I show you the solutions. And
Is 2.25 the maximum stress?
Yeah, the problem is if I open my file, you can see, let me stop sharing and just, okay, just you can talk and then let me open my file, my actual file. So you said what?
Is 2.25 the maximum stress?
For tension or compression? No, nothing. No. No, it's too far. First, find the allowable stress.
Safety factor.
Well, safety factor is 2.25. Yeah. 2.25 is safety factor for all the stress except the bearing. For the bearing is 1.25. Just forget about the shear. Just find the axial and if you have time for the bearing. Yeah, just spend some minutes. If you find sigma AB tension, just you can talk. Just say unmute yourself and say. Then I said whether it's okay, is right or not. And also for comparison. Tension is enough. You don't need to find comparison also. But if you want to find for comparison, as we discussed last lecture, for the comparison, whole the area contribute in the stress. The whole doesn't affect on the comparison. But for the tension, you need to remove that area to subtract the area of that whole, the area of projection of the whole.
And we just use the force of AB that's already given.
Right, right. The force of the AB is
24.
24, right? If you want to find one element for AB, just assume 24 divided by, because look at AB. AB has two sections, right? The 24, half of
Where do you guys
them
get the 24 from?
24 from page number 2. Sorry, page number 1.
So would we have to multiply?
Oh, okay, yeah, I see it. I see it.
Mm.
Would we have to multiply the 24 by 2 since it's 2?
Divided by 2 is 2.
Oh, divided by 2.
Because we have two sections, right? Two beams parallel to each other.
Oh, so the AB is saying that that's a force for both sections. 24. Okay.
So sigma for tension would be 12 is a force divided by area. So the main things, find the area. I would like
the area of AB, right?
Exactly, area for AB, but just for one beam because we have two beams parallel each other, right?
And then you just multiply by 2.
If you multiply by 2, then you need to also use 24 in the numerator.
Oh, okay.
It's up to you. If you use 24, just multiply by 2. If you use 12, just one of them is enough.
Oh, I see.
Yeah.
And then you just subtract the, it'd be 1 inch times the thickness of that.
Yeah, 1 inch
Of that
time.
joint.
Yeah, 1 inch. 1 inch is the thickness of that, and yeah, 1 inch, and thickness is 5/8, right? Yeah.
Professor, why are we not using the FAB instead of the 12K?
You can use that one. You can use that one, 24, but use the both cross sections for that beam. That beam has a 2-piece, right? Look at the first page. Has a 2 beam parallel to each other. If you find the area, just multiply 2.
Okay.
Yeah, you can use 24. That's fine. Guys, find the axial stress, tension, and also find one bearing is enough. Then I can show you the rest of that. And also and also the bearing for that AB, the element AB. So one tension and one bearing. Then I show you out. Just I wanna you think about. I would be happy if you give me a number, then I can compare with my number.
Sigma AB 1.01K.
No.
I got 9.6K.
9.6? No.
Yeah.
No.
Are you taking the actual tension?
Actual tension.
So when you do that, are you just doing the 1.5 times the 5/8?
1.
And then subtracting the diameter of the hole times
Yes.
the thickness, right?
Yes.
Okay. Because you want to calculate it at the center of that hole, right? That's why we're using 1.5.
Yes.
Okay.
Yeah, find this stress, and if you can, then find bearing is, let's see, just 4 minutes, just 6 to 6:25 p.m. Then I can discuss it. I wanna just make sure you maybe familiar with this topic. It's slightly difficult, I think. I would be happy if you give a number from you is a correct number.
Does 19.2K sound about right?
Right. 19.2, is it safe or not? 19.2 is correct number.
I think it's not safe, I believe.
Exactly.
Or
Sigma allowable is 16. It's greater than, it's not safe.
yeah, 16K, correct, is the allowable.
Yeah. And now go to the last page, find the bearing for AB.
Professor, what's the dimension for the top width of AB?
5, top it, yeah, you can see in the first page, in the element of the AB, 5/8 inch.
Okay.
Yeah. I will not share my screen because I have a solution. I don't want to show you this right now.
Which one is the allowable for actual?
Allowable, you should 36 divided by 2.25, right?
Okay.
Guys, 2 more minutes. And then we have 20 minutes to solve this problem. I show you the solution.
For bearing, are we finding it of BC or AB?
AB,
AB.
the same as the tension, yes, right.
So we'd use the same force, right? 12.
Yeah.
Is that 19.2 as well?
Right, 90.2. Is it safe or not?
Yeah.
Yeah, because sigma allowable is 28 point. So, okay, now let's let me guys share my screen, and for the rest of the lecture, just also show this one. Okay, one page, I think so. Okay, so here, I will send you this handout to you with the solution. You don't need to write. So, okay, this is the AB, cross sections for AB, just 12 divided by, now just this pieces contribute to the stress. And here, 2 times 5/8 minus this projection is 1 times 5/8. So which means these two pieces just contribute to the stress. So 19.2, and allowable stress is 36 divided by 2.25. The factor of the safety is 16. So which means this tension is not good. We need to increase this cross section, right?
Professor?
Yes.
How come we don't use the 1.5? Use the 2?
Say that again.
For you do 2 times 5/8.
2 is because this is 2. The total is 2.
How come you don't use the 1.5?
1.5?
Yeah.
Why 1.5?
From the center of where the hole is.
Hole is 1 inch. This dimension.
Right, but there's another dimension on there. It's 1.5. It's from the center of the hole to the edge of the wood.
This one?
Yeah.
It has
Okay.
no effect on the cross-sectional area, right?
Yeah. This doesn't affect. This could be effect on the shear maybe, right?
Oh, okay.
Yeah, we are
I was
talking about
using the wrong
normal
one then.
stress, right? Yeah, because it's perpendicular to this one, right? Does it make sense?
Yeah.
Okay. So for the compression happens on the BC. The only things we don't need to assume the effect of the hole, as I discussed later, because when the member under the compression, they propose the bolt paste to the member, and then, which means we don't need to consider the hole here. We assume all of them, which means the member under compression is not too much critical than the tension. In the tension, when we apply the force, we assume these parts start to separate from the bolt. But here, when it's under the compression help to this to this part, which means we assume all of that, right? So if the sections under compression, just assume whole sections. That's the only difference we should know about the compression and tension. For the tension, we assume there is nothing here. We assume the major element start to separate from the bolt. Then we assume just these two pieces contribute to the stress. But once in the compression, which means bolt paste to the steel or wood, everything, then it means it feel the pin, they feel the hole. Then we assume all. Right? That's the only minor things you should know about that. Right? So we don't need to consider the hole for the compression case. Right? So we solved the axial. Let me first go to the bearing and then back to the shear, because bearing is very simple. Bearing again 12, and now just say the same as this again. Thickness times diameter of the hole. So what is thickness? Thickness is 5/8. Diameter is 1 inch. This one. This is for member AB. For member BC, again, diameter is 1 inch, but thickness is 1 inch. Let's back here. Look, just be careful. For member BC, thickness is 1 inch, but for member AB, that thickness is 5/8. So look, 1 inch is correspond to this, right? So the bearing for the BC is just 26.83 divided by 1 times 1. And 1 is the area of the pin, and the same, okay? That's the bearing. So normal and bearing, does it make sense, these two, before going to shear?
Professor, quick question.
Yes, sure.
So we don't have to assume two members for the tension. We can just do one.
Yes, we can assume two, but if you assume, you should use the 24 in the numerator and then multiply the denominator by 2, because we have two sections, right? So for simplicity, I just focus on one of them, but you can use 2, and but the force would be the 24 here, right?
Got it. So you would have that, since there's two members in it,
sure,
and then you could do each one.
Yeah, because these two members get the same.
Okay.
Yeah, right.
Professor?
Sure, yeah.
How come for the axial tension and compression, you only solve for AB or BC, and not both, how you did in bearing?
Because AB is under tension, we find from statics, right?
Oh,
and BC under the compression. This is the first step, right?
Yeah.
Okay, now one thing left is shear.
I had a question.
Sure.
Back to axial tension. I get that the 5/8 is the thickness of the member AB,
Yes.
but I don't get where the 2 and the 1 come into play.
These two?
Yeah, the 2 and the 1.
This
The
two,
denominator.
this two is the this thickness, this height of the member, this one. This two.
And the 1 is like the width.
One is the diameter of the hole,
Oh,
right? This diameter of the hole, right? Here
okay.
is given 1 inch pin. This 1 inch pin means the pin has a 1 inch diameter, right?
Okay.
Yeah? Does it make sense?
Yeah.
Okay.
So I don't know if this has been asked before, but why did for actual tension we only use 12, and then for actual compression we use like the actual force bond with statics, if that makes sense?
Because for compression we have one member. Member BC is just one member, right? Just one cross sections. But for AB we have 2 cross sections.
He said you can also use the tension force.
We can use 24, but you need to multiply denominator by 2, right? Does it make sense to you?
Kind of. I don't know if I'm just getting confused in the fact that
Okay, what's
the
your
force.
what's exactly your question?
So force AB it's 24, and then we're only using 12. Is that because we divided by half, or is it just a coincidence that
Yes.
FAB is 24, and then the force that we're using is actually half? I don't know. If that makes
Yes,
sense.
yes, because element AB has a 2 beam parallel to each other, right? So half of the 24 goes to this beam, half of the 24 goes to that beam, right?
Oh, okay, that makes sense. So we're actually using the force AB that we found.
Yes, yes.
Okay, thanks.
So based on the direction of the force that you're using, that decides the cross-sectional area?
Yes, exactly.
Gotcha.
Yeah, exactly. So let's go to the shear. This is the rest of that. And then if you have question, we can again continue. For the shear, it asks us to find the shear in AB and the pin. So for the AB, the same as this picture, right? So there is a force here. These are the plane of shear, right? One plane of shear here, one plane of shear here, 2 plane, right? So here, just for AB, we have one hole. So one plane here, one plane here, these 2, and these are the plane of shear. So what is the dimension of that? Now is 1.5. One of you asked me earlier. Now look,
I used that to find the axial, and I got a different answer.
Yeah, this is 1.5. Now this 1.5 is contributed to the shear times 5/8, right? This one. And since we have a 2 plane, just multiply 2.
So that 1.5, it goes from the center to the edge of the
exactly, yeah.
beam.
Yes.
You would only use that for shear.
Exactly.
And for the axial, it's talking about the whole beam, right?
Yeah, because the force is parallel to this plane. That would be the shear.
The force of the
AB.
Of AB, okay.
Right. And the next thing, it asks us to find the shear in the pin. So then shear under the cross sections of the hole, right? So the force in member of BC play the role of shear on the pin. I don't know, you can imagine. Look at this member BC. Member BC is cut this pin. Pin goes perpendicular to the connection, right? Then the member BC cut the holes. So it asks us to find the shear, the force in the member BC is 26. And we have a 2 area for the pin, one here and the other one the other side, right? So that's a PD squared divided by 4, and 2 means we have a 2 area, one here and the other one there. And this is the force of BC, so this one. This member BC cut, it make the shear on the hole, right? We assume that one. We can find the shear based on the force in the AB, but this number 26 is greater than 12, right? And the cross sections of the bolt would be the same. If you find that one for sure, that shear stress in the pin would be less than that one. So because of that reason, just we find the shear stress based on the shear stress in the bolt based on the force in the member BC, because it's just 26, right? 26 is greater than 12, right? So, but no worry. If I give you this problem to you, I just ask you, find the tension in AB, find the tension in BC, find it, for example, shear in pin, find the shear in AB, something like this. Not like just find everything or check is it safe or not, right? If I give you this problem in the exam or something like that, I just ask you also, for example, set part A, find the axial tension at member AB. Part B, find the compression at, find the axial in the member BC. Part C, find the shear in AB. Part D, find the shear at the pin. For example, part E, find the bearing in AB, find the bearing in BC, something like that. I just said by details. So I will not ask you check everything and say, is it safe or not, right? Just no worry for that, no worry for that. If I wanna ask you in the test, something like that, I just maybe ask you some of them, maybe just 2 or 3 of them or 4 or some of them, and just and say in some individual parts. Because if I ask you something general, this is maybe confusing. Are you going to post? Yes, I wanna send this one just immediately after the lecture. So guys, so we have some minutes. If you have question, ask me about this.
Can you go down to the axial compression?
Axial
I just want to check the area, how you did that one.
Yes.
Okay, so you always use the total thickness and total
yes,
width.
exactly. Yeah, the reason is once you just imagine, you need to imagine. We have a member and the bolt on there, right? When it's on compression, that bolt, it fixed to the member. It means we have a uniform section. Then we don't have effect of the hole. But once we have on the tension, these piece it start to separate from the bolt, and the bolt pressure to this edge, and then just these two contribute in the stress. Yeah, just because of that reason, they propose just use the net sections of the element for the tension, but for the compression, assume whole of them, including the area of the what's that whole pin, right?
You said you include you don't take out the area of the hole in compression because it has no effect on the bolt,
right?
But in tension, you're saying it affects the pressure on the bolt, so you have
to
subtract that area. Okay.
So let me guys just stop recording. Then if you have a question, we can continue. But let me just stop recording.